Yes, we're late. All right. So, how's it going, everybody?
Awesome.
Awesome. You can call me awesome. That's fine. One thing I wanted to pull up was something I hear the special ed students might have questions about. I have a few homeworks that I finally got busy. First of all, homework 4. Thanks for your patience with that. I created a homework 5, which is out there. Homework 5 is effectively do homework 4 on your own data again. And I put a due date of December 1st on it. It's like what homework 2 was, homework 3 was. Remember how homework 3 you had to take your data and do CFA on it? This is take your data and do CFA, but with categorical data, ordered equals. Now, if you don't have that that type of data for this, I know some of you had actually continuous data. Talk to me, we'll find some way to make this work. Yeah.
Is it going to be binary or continuous?
Could be either.
Okay.
Mm-hmm.
Simulation is always okay.
Yeah, you can do that too. I'm less. Here's the motivation. All right, if you fulfill the motivation, I'm happy. I want you to take what we've talked about and take what you did for that terrible homework 4 that didn't work out very well, but just have some experience with doing it with your own data or some data in general. Mainly because I want you to understand how to the practical side of doing this. That's it. Whatever fulfills that. If it's you simulated data and you apply this to it, totally cool. If you want to borrow some data, totally cool as well. But you don't need to have the bottom line for this homework is it's effectively the same thing you did with CFA. It's just and some of you have Likert scales to do it. I think a couple of people in here don't. And if you don't, or maybe if you have some other data that you have Likert scales for, that's fine too. But if you don't have a Likert scale or you don't have categorical items, we'll find a way to make it work. Any question? No, sorry. No worries. It's funny because I saw the hand exactly in the field of view where it would look like that's like the cool way of asking. Michael's like, yeah. I'm just too cool to raise the whole hand. Yeah, I get it. I get it. Thank you. So does that help with homework 5? Again, I put December 1. Honestly, I don't care. If you turn it in December 1st, I'll turn it around to you. You have a chance to revise it if there's anything wrong. This one is pretty. There's not going to be plots. It's going to be make the model fit and show me your parameters. And the large reason for that is there's not a lot of good functions built into Levon already to work with IFA. But I just want you to work with it. So that's why I put December 1. I don't think it's going to be overwhelming. I hope it's not. But again, and if you want an extension, you got it. Not a problem. The last day of extensions that I'll give is like the end of class, like December 15th. I don't care if you turn everything in on December 15th. Whatever. Does that sound cool?
Can you use Merge?
The model fitting process is different there. I didn't talk about how to check it. So, no. What?
I know how to do it in Merge.
What do you use? Can you pull an RMSE out of Merge? What?
Yeah.
Yeah, you have?
Yeah.
Okay, well, if you can do that, then yes.
Right.
But you have to use the M2 fit statistics.
Yeah.
So, all right. Does Billy teach you this?
No, but you can do it like through.
You have it, and you have an example. Yeah. Okay. I was gonna say you're in Billy's IRT class,
Yes,
right?
yeah.
All right. Okay. Just checking.
Homework 6 is already available.
Yes, it
online.
is.
So when can we start working on that?
Immediately.
No, like based on we have the Richter so far, and then we can answer it.
You can even start on it right now, because homework 6 online is measurement invariance with CFA, and it's complete CFA, and we've already done some of the sections. Right, we talked about configural model. There's the metric invariance. There's a scalar invariance. There's a residual invariance, which we'll talk about today, and then there's the factors. Like what was the actual thing happen? So you could start on it now if you wanted to. Is that, if you want to? I don't want to overwhelm you. It's not.
No, I'm just.
And actually, I have on here December 1 as a date. I actually put the date for whatever reason I didn't update my website, but the date I had put on in the database, which is the thing that checks the homework, was December 8th, like a week later, than December 1st. But I don't care. You could however you want to do it.
No, no, I need earlier.
I need it earlier. Okay, pretend it's December 1st.
Yeah.
And if you can't make December 1st, just let me know. It'll be fine.
Okay.
No problem. And then homework 7 is, I debated having this be optional, but I think I just want you to have some type of practice with doing some type of structural equation model. And that it's effectively, there's lots of ways that you can do this. You can take your data and do a measurement invariance. You could take your data and do a structural model, which we haven't gotten to, which is the thing after we get past invariance. A path model with the latent variables, a path model with the observed variables. However you want to do it, like an actual structural equation model is the last one. And I just put the deadline of it on this December 15th. There won't be a chance to do revisions on it, but if you work with me ahead of time, if you have questions, if we could just kind of talk your way through it, I'll be happy to make sure you're on the right track for it as we move along. What do you think? Hatish, TJ, did that help? Does that answer your questions about homework? Other thoughts yet? Good.
December 15th should be a Friday.
Yeah, sorry, it's not Tuesday. It's a Friday. I'll update it. Yeah, Friday the 15th. Yes. You see, like when I'm doing this, I'm like, it's very goal directed. I need to check this thing off, and so I check all the items and make sure this is what I want to do. Yep, that works. Okay, great. And then I change the date, and of course I don't even look at the. I'm so focused on changing the numeric date that I didn't see the word right in front of it. So my apologies.
So homework 7 is essentially like our final.
Yeah, it's the final deal. The other thing I want to note is we had that quizzes thing that I talked about in class. We had one quiz, and I gave you all the bonus points for it. Here, what you should see when you go in to your homework is that you should have all 12 in class appointment. I have given you an early holiday present of some sort. All right?
Thanksgiving.
So that one quiz that you did before, I told you it was worth 2. It turned out to be worth 12.
Wow.
And you all did well. All right? Well done. Because I don't want, this is not punitive, and I feel like everybody here, I didn't change that date. And that one's an ASP code. So that's, whenever there's stuff in ASP code, I can't spell check it, and I can't change the dates. So oh my goodness, it's a nightmare. But yes, you should see 12 added to your points there. And if there's a question on your points, don't worry about it. Please ask me about it. I'm not trying to indiscriminately penalize anybody in here. I think everybody's going to get an A, and we'll move on. My biggest concern is less your grade, and it's more your ability to do what we've done in class. I want if I were to see you in 6 months when you got out of here, and I were to say, hey, I need some help with the CFA project, if you could point me in the right direction, that's what I want you to be able to do, right? Or, I need to go back and look this up, but here's what I think is going to happen, right? We don't ever test that afterwards, but I feel like there's got to be, and maybe you can help me with this. There's got to be there's a sort of a relationship between how much you can actually hands-on practice something and then go and do afterwards. So I feel like there's several people that if we have good slides and we give a good coherent lecture, students walk out thinking, I got it, I can do this, right? And then when you actually sit down to do it, it's a lot different, right? So I want to give you both experiences. That's it. So anyway.
You have done video.
Pardon me?
You have done that.
I hope so. Yeah, I hope if I come to you, I will come to you 6 months from now, and I'll be like, hey, I've got this CFA project. Can you help me? Yeah. Ahmed, I know you're working with the Spear group. It's like, I want to see you in Spear published, but not only that, I want to see that like you're bringing a new level of like analysis to the Spear group. So that would be cool to see. Yeah. So anyway, that's my motivation in doing this. That's where it comes from. I honestly think again, grad school, the grades are already not a big deal. So. What do you think about that? Does the homework? I mean, so thank you for the feedback, yeah. But I mean, just in general, does the homework give you at least enough practice to see where the pitfalls might be, and sort of the training wheel approach of these stupid red boxes, training wheels. But you know what I'm saying? Like they let you know if you're in the ballpark. They should let you know if you're in the ballpark, with the caveat of I need to make sure the analysis is right on my end, which is frustrating, I know. But that's the motivation for it. So we'll see. Okay.
Especially when we use our own data.
Yeah, that's it. Like, it's real easy to take. That's the other thing about teaching these classes. It's real easy for us professors to create examples that you don't have to do a whole lot of work on to get into R. I try to give you a starter file, and or to. Speaking of, did I drop it in here? Oh yes. Whew. Okay, you can actually do homework 6 because that was one of the mistakes I made, like in homework 2. Was the zip folder there. So that, yes, it's very easy for me to give you things that sort of work out of the box. And when you work with your own data, things, all sorts of things happen. Yeah.
Yeah, just like for the class, like who did homework 1, I think those people are eligible to provide a workshop about CFA with the CREMDA.
Oh, that's cool.
I attended the workshop and we talked about this. Like that homework, it's enough to do a workshop like that.
That's awesome. Yeah. That's great. And that's the thing. It's like we try to walk a balance. It's tough teaching a quantitative classes because there's so much that it's not although I love the discussions we have in here. But it's not that discussion based class, but it's not discussion, and it's not the hands-on and like some of the classes. I don't know the classes in counseling, but some of the things I think that are happening, the really intensive classes that you get in your field, where it's sort of a practicum, or it's you've got like a real intensive working relationship with the faculty or the TA or something like that. We're neither of those, right? So how do we walk that balance of giving you something that's challenging without overwhelming? And I don't know. I can tell you that in my multivariate class, I know my first homework is actually way too overwhelming. So I'm trying to think of ways to. That's why I'm talking about having a flip class or having something like that. Did you find homework in multivariate overwhelming when you were in it? Yeah. Michael, yeah. For me. I ended up like
pseudo tutoring several of my peers,
and
that was the most helpful experience for me.
Cool.
I internalized a lot of stuff because of what I helped.
Well, and I know you started using it. We had conversations. I saw you using that outside of class as well, and so that really helped too. But yeah, you're right. I want to find a way to sort of walk back the. I know when it's too much, and I know as the class sort of went on, I sort of tried to bring it back a little bit. But yeah, how do you walk that line? It's I don't know if there's ever decided, right? So, everybody else, what was your other 905 experience like? Anybody?
Not yet.
What?
Not yet.
Not yet. You're taking this for what's it?
For me, a couple of my friends, we taught it in the psychology department.
Oh, I see.
And it's we don't have like a lot of problem with the concept itself, but how to do the calculation using R, and the teaching assistant was very helpful.
That's good.
Explain everything in details and walk us slowly. So
it was well organized.
Very good. Very good. How about those of you?
In the lab, that was really helpful.
Oh, that's good.
Yeah.
Weekly.
This is very helpful.
Yeah. With those of you in 905 last year, how did that go? What's that? No. Did you get a little homework or no?
I think I did not like the room.
Oh, the room was terrible.
Foremost, I hated the room. I felt really disconnected with Billy. And then I wear glasses to look at the close there, but I couldn't read.
Oh yes,
with he was showing, and it's too far away, and I'm like, so it was disconnect. Yeah. And then the homework, I wanted homework a little early on to check for understanding, but.
Okay. I'm just trying to understand where the line is, because I know, and Michael was in my 905 class. I know that when I gave that early on homework, it had the effect of really making everybody really anxious. And I didn't want that. It was too much on the side of it. And then there's a lot of things going on. There's R. Everybody comes in with a different preparation from your ANOVA regression linear model sequence.
Maybe short check for understanding type of thing.
Yeah.
Helpful, even related to concepts.
Oh, cool.
Not that, R related, but
just the concepts itself, yeah.
Just kept on and on without me fully understanding the concepts of what Billy was talking about.
Okay, so that's good feedback.
I felt
feedback.
left behind.
Okay, well let me. I'm going to try to fix that. That's the other reason why I was thinking about flipping it. Sorry to keep taking our class time for it. This also whatever feedback you have about this class, I'd love to hear too. But is that I'm hoping that with having more hands-on time in class, that overcome a little. Some people will overcome a little bit more, have more experience with R, guided experience with R, but also you'll have more experience checking. Okay, now what does this mean? Now what does this mean? Now what does this mean? Right, and so hopefully that would be valuable, but we'll see. Cool. Sorry to belabor the point. Thank you all for your feedback. I appreciate it. It's a tough thing. Okay, should we get to the discussion, the topic of the day then? Yeah, I know. Looking at the clock, I watch you. So I know you got to leave. I'm sorry.
It was not a critique of the session.
No, I hear you. I hear you.
Appreciate the discussion.
I'm the look on everybody's face. It looked like you were into it, and nobody's checking their phone. But you know, I just I get it. It's sort of tangential. So we were talking about measurement invariance, and we built the idea. We started with the configure model where everything is different. Remember that? And then we locked in the factor loadings, and we did a likelihood ratio test to see if they were different or not. And where did we leave off? We did scalar invariance.
My last note says make sure stuff you want to be equal is equal.
Oh, yes.
And lock in your intercepts.
That's right, yes. The toughest thing with this... Oops, you don't want to see the homework folder. The toughest thing with doing this, I've found, at least for someone like me, that I struggle with the attention for detail part. I really do. And so there's a lot of copying and pasting of code that goes on, and it's almost like... What's that?
That creates a lot of problems.
It does, and for me, it's a recipe for disaster with knowing how my visual search goes. So that's why I was saying. So let's go through the example real quick here. Once again, we started with the configure. This is the data that came from the Brown Chapter 7. There are 9 items rated from 0 to 8. We're using the CFA models, which we're pretending these are continuous. We have our configure model syntax where every group gets a separate set of parameters. That's sort of our overall baseline model. We want our subs, and here's just another tidbit on that. We want every one of our subsequent models where we start making things equal across groups to fit as well as this one. So that's what we're always checking for, right? When we start constraining parameters to be equal, we go back and we check, hey, does it fit as well as the configure model? It should, right? So that's our baseline. We then went to metric invariance, which involves the factor loadings. So now we changed the label in each group. We ran the analysis, and lo and behold, the thing that never happens when we do the likelihood ratio test comparing configural and metric, the p-value is not significant, indicating that the metric estimate, the model with fewer parameters, fits as well as the model with more, the configural model. Right? By the way, that's why I think this is simulated data. That never happens. Usually the whole invariance thing just makes you want to just pull your hair out, at least me, at least. So we then moved to scalar invariance, which is all the intercepts and the loadings. And so here, and I forgot to mention, let me go back. In the metric model, not only did we change the loadings to all be equal across groups, but we also changed the factor variance, so that in one group we fixed it at 1, and in the other group we estimated it, and that's that NA for the syntax that's a little weird.
So, because we had a discussion last night about the computer and the matrix model, what I imagined, theoretically speaking, that for the computer model, there will be 2 distribution of for each group representing the low factor loading, intercepts, and variances. And for the metric model, there will be one distribution with one standardized metric to judge if they are different.
That's right. So our factor loadings, because they're constrained to be equal, there's one set of them. But by having them be equal, effectively we're saying the factor is related to the item the same in each group.
And when you anchor the variance of one group, you estimated the other one to be to revolve.
That's right. It's a multiple of the variance itself. That's right. Yep.
So it will be in the same metric.
That's exactly right. Yeah, so and that's part of the reason why we have that one group's anchoring at 1, because ultimately when we get that variance estimate, we can talk about it as being a proportion of 1, right? So when we look at our variance estimate of 0.863, we know the variance for the male group is 86% the size of the variance of the female group. And that's where I changed the number. If we made it a variance of 100, we'd see a variance of 86, right? So it'd still be 86% of the size. Okay, so then we went to the scalar invariance model. We then locked all the intercepts to be equal in each group. And we estimated the factor mean now for one of the groups. And we can first off look at the estimates themselves. Here we see the factor mean in the male group is 0.112 less than the factor mean in the female group. And this is an interesting thing because, and this is sort of where the terms metric and scalar get their derivation from, I think, but I may be wrong about that. I still don't fully understand why they use the word scalar when they do. But the idea that this estimate, this is not saying that the mean for male is 11% of the mean for female. It's literally saying the actual mean difference, right? So it's not a proportion of it. So if I changed the anchoring mean to 100, what you're going to see is, and estimate this, and I estimate the factor mean for male, you'll see that the factor mean, here, let's just double check. The mean for female is 100. The mean for male will be, oh wait, what's this? Negative point.
It's not the difference.
It should be a difference. What's going on? Did it break? Did I do something wrong? Yeah. Well, maybe I'm not understanding this the way I need to be. Off the fly example. Nope. Oh wait, I have a big standard error. It's having an estimation issue. Let's back up. Take 1 0 off of this and try this right here. What you should see is, if it's a stable estimate, then the mean is 0.9888. Which, if you look at that, if you look at the difference between the means, it's negative 0.12. It's literally that far away, right? So as before, with the variance, when the variance went up to 100, for one group, when we fixed the variance at 100, the other variance corresponded by just growing to the size proportionally. Whereas the mean is not a proportional thing, it's an actual absolute difference between the two. And I think that's again, I would think proportional would be scalar, because I think if you think of a scalar in a matrix algebra sense, it rescales a vector, it changes the size proportionally. So I don't understand why they call factor loading scalar invariance, but then again, there's probably a good reason, I just don't understand it. But that's sort of the difference between the two. I'll put this back to 0, and let's go and test whether or not this model fits as well as the other model. We look at the ANOVA result, we see, or we use the ANOVA function, we see the metric estimates and the scalar estimates. Here, this p-value also suggests the model fits roughly the same as the metric estimates. Had I gone a step further and done...
So in this case, we will go with the metric estimate, because it has like...
we go with the metric estimates we would go with because it has fewer parameters, right?
Yes.
Mm-hmm. But if I did the same thing, what's that?
Parsimony.
Pardon me? Parsimony. Yeah, we think it's more parsimonious. If I did the same thing with the configural model, you'll see that this is also very close to it. So, actually, hang on. Let me just double check. Yeah, we're in scalar right now. I want this to be scalar estimates. So not only do we fit roughly the same as the metric model, we also fit roughly the same as the configural model. That's what it's saying. So in this, just to show you what would happen if things are off. So this data is really too good to be true, I feel like. But if things were off, let's just kind of go through what would happen. Let's pretend our p-value was, yes, Jihong.
Your R markdown says object no font, maybe your assignment, the model name
is not right.
Uh-oh. Where is this? On the online one?
Yeah, online one.
Okay, I'll have to fix it. Sorry. Hang on, let me make a note.
Either ANOVA, magic estimate, and the scale estimate.
Okay, got it. Thank you. I will fix that after class. Here, let's imagine this didn't fit well, right? If this didn't fit well, this p-value was small, what would we do to fix it? Again, what we can do is look at the modification indices. But the modification indices to fix things in Lavon are tough because, sure enough, they don't give you all the information you need unless you put in some seemingly arbitrary and not needed commands. So if you leave these two options off, it doesn't tell you what you need to know. So when you get to the modification indices, add free.remove equals false and maximum number equals 10,000, and it will give you all the modification indices you need. So this result right here is really a lot. There's a ton of information. But what I then do is I try to restrict only the ones that are needed in this step. So we're going to look at the modification indices only for the intercepts for the items. And that's this operation equals this tilde1. If you remember in syntax, the intercept syntax was tilde1 was the intercept for an item. And that's how we read the modification indices. So when I push play on this, this is the list of modification indices. You'll see there by block, it says block 1 and then block 2. Block 1 represents the first group that shows up in output. Block 2 represents the second group. And you'll note that each of these talks about whether or not you free one of these modifications, one of these means. But because we have two groups, if you free the mean for item, if you free the intercept for item 1, you're effectively doing so, and you can only free it, once you free one item's intercept, you effectively freed the other two. Right? So this is sort of redundant information in some regard. What I do when I look at this is I look for the largest, I look under mi.scaled, and I look for the largest modification index. In this case, it's item 7 for group 2. So it tells me if I were to modify my model, the first place I'd go to is item 7. And because I only have two groups, if I modify item 7 for group 2, effectively I'm modifying it for group 1. And you'll look, those are the two that have the two highest modification indices.
When you say modify, what do you mean?
I would go and free the parameter. Right. So I would go make this what we call a partial invariance model by allowing the intercepts for item 7 to vary across groups. Now, once again, to be clear, this result, with the p-value being very high, I would not do this normally. I'm just doing this to demonstrate what happens when the model starts to break. So how I fix that is I go to the offending item here, item 7, and I just change the label so that they're different across groups. All right, so item 7 right here, the label before was just like the label you see above it. It was I7, I7, right? So now I just go and relabel it I7F and I7M.
Like for male,
That's right. That's right. So first group is female, second group is male, and that's where it shows up in this clunky syntax. Now I will note in the process of invariance testing, yes.
So by dividing F and by specifying F and M, that means we are freeing.
We're freeing the yeah. It's going to because it's going to estimate them separately for each. We'll have one more parameter in this analysis than we had in the full scalar invariance model with the intercepts before.
And the parameter will increase 1.
That's right. The parameter will increase 1.
Will decrease 1.
That's right, yeah. The parameter for this one, well, there'll be one more parameter than the last analysis, and then when you do the ANOVA result, instead of seeing 8 degrees of freedom with the metric model, you should see 7. And these are all good things to be thinking about, again, because remember how we were saying you should check what needs to be, what you think should be going where. If I run this analysis, the first thing I'm going to check is item 7. What's the mean for an item in group 1? What's it for group 2? So the other thing I'm going to do is just to look at the intercept difference. I just created a brand new parameter between these two, but that's just more just for comparison purposes. If I run this analysis, yes, the ANOVA does. There's the error. There we go. So I run this whole analysis right here. Let's go look at item 7. Item 7's intercept, pardon me. Item 7's intercept, you'll see for the female group is 3.869. For the male group, it's 3.493. So we achieved what we wanted it to have. Now let's take a look at the model fit one more time. What we can see is that this model compared to, why do I have scalar estimates 1 and 2 again? That's right, we're a scalar estimate 2. Our model compared to the metric model. So scalar estimate 2 is our model. We compare that with the metric model. We see that the p-value gets even better, and there's the 1 degree of freedom change, right? It was 8 degrees of freedom before, and now there's 7. There's only 7 now because we've added 1 more parameter. So it's one parameter closer to that metric estimates model where we had all the intercepts estimated separately. If we compare that with the scalar model we just ran, where all of the means, all of the intercepts were equal, there's a 1 degree of freedom difference with that, and that's literally the item 7 parameter. And we do see that this model is not the same as it, right? And what that means is our model, scalar estimates 2, fits better than the model that showed up before. It's a significant difference, which is interesting because if you think about it, the chi-square, or the likelihood ratio test before, said that our model fit roughly the same as the metric model. Let me put some more ANOVA statements here. If we were to compare estimates 2 with metric estimates, and if I were to compare this last model with the configural model, let's see how the fit changed there. So comparing it with the metric estimates model, oh geez. So comparing our model with the metric model, you see also it fits just as well as the metric model, and it fits just as well as the configural model, which is interesting because our model now, when we compare it with the previous scalar model, it fits better. Right? So it's this odd, weird combination of fit tests. But basically, we're getting better at fit. Questions? Okay, the next step in the process is to look at, well, here I can just go over my slides. The next is residual variance. So backing up a little bit, the metric model invariance, where we took a look at the factor loadings, you notice that really impacted the variance of the factors, right? The scalar model where we looked at the intercepts, that really impacted the mean of the factors, right? And those are the two things we need to be concerned about. Like if you're interested, if men and women differ in this scale here, you need to understand whether or not the means if there's a significant difference in means of the two groups for the factor, and a significant difference in variance, right? If the variances are significantly different, you have a heterogeneous test that you have to worry about. Actually, it's all built into the analysis anyway. You don't have to worry that much about it. What about residual variance? Where does that matter? Well, it matters. It is error. It talks about how reliable each test is effectively in each group, right? And you think about why that is, or residual variance, we talk about how much information each item has, right? We learned in IRT information is sort of the reverse, or sort of the more information is, the more reliability there is. In factor analysis, information is factor loading squared divided by residual variance, right? Well, if we know in our analysis now that the factor loadings are identical across groups, but perhaps the residual variances might vary, what that really means is that there may be better reliability and precision of measurement in one group versus the other, but we're measuring the same thing. Does that make sense? a little bit?
Can you repeat that again?
Yes. If we don't have residual invariance, it just means that our scale, while it means the same thing, if we've established partial metric invariance, we basically have established that the scale means the same thing in the two groups. The factor is the same trait, but that if in one group we have a better reliability at measuring it than the other group. That's all that we're saying. So the question then about residual variance tests then becomes whether or not they're actually necessary, right? If you think about it, if the factor loadings influence the factor variance, they're necessary, because if we don't have any of the factor loadings be tying together, we're not sure the variances of, we're talking about different things altogether, apples versus oranges, right? And then also the item intercepts, they influence the factor mean. We need some of those to be on the same metric as well to be able to say the means represent the same thing too. Okay, we did that. We've got mean, we've got variance, there's nothing else left to have. Right? So residual invariance sometimes is called strict factorial invariance because when you test it, you're sort of going above and beyond probably what's needed to establish the claim that that you're comparing the same trait across the groups. So oftentimes, in fact, you'll even see this, particularly in homework 6, none of the items, residual invariance, you'll just find this out, and this is no secret. Residual variance, there's no equivalence on any item in any of the groups. Well, this homework 6 is comparing students' feelings about gambling to gamblers' feeling about gambling. And you can imagine that one group's going to be a lot more variable than the students. The students are strongly disagree with everything. Their variance is much smaller on all of the items than the gambling group. So because of that, okay, we just have a better reliability for one group than the other, but once we've established partial metric and scalar invariance, we're okay to keep going. So, let's see here. How do we test it? Same thing that we tested before, the same way that we tested it before. Now we go to the residual variances themselves, and we constrain them to be equal. There is one caveat, though, and this is a caveat that would have carried through from the very beginning, but none of our items were non-invariant. Everything was found to be invariant when we looked at factor loadings. But anytime that you find an item that has a factor loading or an item intercept that's non-invariant, where you have to estimate it differently for the group, in factor analysis there seems to be sort of I don't know if it's a debate or a tradition, it depends on who you talk to, but oftentimes what people do, the reason why is that these are independent, right? In a normal distribution, the mean and the variance are independent. So what you do to one should not affect what you do to the other. So there's less of a debate and more than just practice. But ultimately what we end up seeing is once you declare an item to be non-invariant somewhere in the model analysis, it becomes non-invariant in the remaining parts of the analysis as well. So item 7 we saw, just to give you the example from the last time, we saw item 7 was non-invariant. Even though we probably shouldn't have done that, it was more just a didactic thing, a tool teaching instrument. Because it was non-invariant on the item intercepts, we're going to allow that to be non-invariant on the residual intercepts as well, the residual variances as well. So it'll be different. And had we seen, for instance, item 5 had different factor loadings, item 5 we likely would have left the intercepts different and the residual variance. So once it goes non-invariant, we just say, all right, that one's non-invariant, let it go. All right. There is some debate on that, although it's not, oftentimes it doesn't really make a difference. There also is some debate depending on how you do it in IRT, but none of this applies to us because we're in Lavon, where we're in least squares world. It pretty much functions the same way here too.
So it's kind of like when you say that if item 5 has non-invariant, would affect like the intercept of
right.
Item 5. But we have no item 7 and it's
right. So we left because we found the slope. And this is the part that's interesting about it, because we're picking this order: item factor loadings, item intercepts, residual variances. Item 7's loadings are fixed to be equal, whereas these other ones are not. Which is sort of, again, silly, right? Because it matters the order we're testing it. So ultimately, I come down on it. You can lock in whatever you want, particularly in factor analysis, right? But I'm just trying to show you a convention, right? In my mind, and I don't have the proof in front of me. So I'm trying to weaken my argument here, but I can sketch out a thought mathematically why I can say, yeah, I can estimate this model and it's not going to hurt me, right? When they're both the same residual variances. I'm mentioning this to you because not everybody agrees with that, and I would say convention is more often the case. Start with the factor loadings and move forward sequentially this way, and then in steps of the process, when an item becomes non-invariant, the remaining steps that it's non-invariant for. So, but yeah, does that help? It's sort of weird, right? Why are we letting the factor loading stay the same when we're not? Personally, I want as many of these things to be the same as there possibly can be, right? Because it strengthens my argument that the factor means the same thing in both groups.
So when you say, let us assume that they administered an instrument, and I would like to the instrument, the response of the two groups like to be different, totally different, like and to establish the non-invariant aspect of it. How we can look at the residual? The interpretation now is
one group is more varying in their responses. That's basically it. So, and we'll see this in the gambling data, right? The gamblers, there's a lot of variability whether or not they endorse an item. The students, everybody does strongly disagree for the most part. And so because of that, residual invariance tends to be different between the groups. So
residual invariance, the more the reliability would be more established in the students.
Yes.
Compared to the
yes, but it's a silly thing because everybody's at the bottom. We all know they're at the bottom. Yes.
Because the variance there
is shrunken. Yep. That's right.
And this is also related to like IRT when like
That's right. The test information function will be very different between the two as well. So one thing I'll note, in this example, we also had the residual covariance between the two. This is item 1 and item 2. In this step, technically speaking, there's nothing wrong in testing this simultaneously, but I'm going to break it apart. So we look at the residual variances first, and then we do another step with the residual covariance. There's nothing wrong doing it simultaneously. I'm just trying to slow down what we're talking about here, right? So again, we can run this analysis. We can take a look that our residual variances are the same. 1.447 here and 1.447 here. The only difference is 4.629 versus 3.653. Let's take a look at our likelihood ratio test, and sure enough, hey, residual, it works. We're fine. It's the same in both groups. There's a part when I teach multi-level, when I get into cross-level interactions, that people start cheering for non-significance. It means they don't have to interpret that. We don't have to talk about what it means. Like, they're so weary from doing all this damn testing. They're like, ah. So we're not here yet, evidently, but we're going to be. So we're going to leave it like that, and we're going to move on. Next, let's take a look at the residual covariance. We're going to equate it to be equal across groups. We're going to take a look at this. Oh, there's a small p-value. Okay.
Disappointed.
That's okay. We'll just change that so that we'll say, you know what? We're going to leave it separate by group. So ultimately, when we're done with this step, we're going to go, when we do our next model comparison, we're going to compare the previous model where we have all the residual variances equal except for item 7, and then the residual covariance unequal. Mayumi.
Oh, I don't. It's still hard to switch this from significant to non-significant.
Yes, it is, isn't it?
I'm still struggling. So, but anyway, because of the sample size,
yes.
you set the code before, like, my question is that because of regression and stuff like that, we set the alpha level first, and
yes.
then maybe because of sample size, this is not, considered that important. Wait, is there anything like this in this situation, or this is just
it's very nebulous.
Okay.
Realistically, You think, when we talk about what the p-value should be, for instance, for one of these likelihood ratio tests, we're doing so many hypothesis tests, right? The chance for type 1 error is quite high. So, I would say, my own personal feelings about this, I go through this and I want to see a p-value, it's like 0.001 before I really get worried about it. But not everybody feels that way. So I'm sort of giving you the demonstration of if we have a type 1 error that causes us to free parameters across the group, ultimately it makes the mean difference in the factors harder to describe. So it's like thinking, well, type 1 error here doesn't hurt us as badly because it's going to cause us to put more parameters in to better describe the model. But there's no good described. I don't feel like there's a really good described process as to what needs to be there. People are doing all sorts of stuff. But I think a rationale, describing what your rationale is important. So here's why I said it this way. I was concerned about multiple comparisons, and so I said a very low p-value just in case.
So maybe you can do the alpha level adjustment to state your rationale. How many comparisons you are going to?
Yeah, well, this thing, you don't know how many comparisons you're actually ultimately. Yeah.
Let us say maybe you know after you've done the analysis and you.
Oh, right, I hear.
So you come back. So using this technique, because we want to control type 1 error. So we adjust for the alpha level using like Fanfroni or other.
Right. Yeah, you could do that. I don't know. I just pick a low value and call it good. Pick a really small value and call it. That's what I do. 0.001, saying that ultimately, even if it's inflated, it's not going to be a 0.05 or more. It's hard to say because ultimately, every time we look at the modification index, we've done basically a hypothesis test for every one of those parameters that shows up. Right. So we could probably jot down the permutations of how many. Doing the math on that for me is hard. I don't know ahead of time. It's sort of this, and we've got this forking paths of where the p-values, where decisions will change based on what we've chosen with the p-values, right? So if we had, like we saw when we freed the mean or the intercept for item 7, all of a sudden the number of modification indices got smaller for the next step because we didn't have it there, right? So there's another, it's not as easy to compute. There's going to be 800 hypothesis tests for this. It's really going to be something that depends on parts of the analysis as well, which is sort of scary. But I think being really, really strict and conservative with the I like that personally. But I don't know if I'm in the minority on that. You'll see in practice, people do all sorts of stuff. It's just have a good argument. If you can do the number of tests you have Bonferroni, that's fine.
Actually, why not like stating it logically by using like a mathematical equation?
Oh, you could, but what I'm trying to say is you don't know the outcome of the mathematical equation. Because the number of tests you're going to have is going to depend on the sequence of the process.
I know, but if you are going to say like there might be, my understanding would be that there should be like for R, an embedded like function to say that if you use like one comparison, the alpha level may be 0.05 because you cannot go or 0.01.
Right.
Then if you use 2, this is the value. Use 3, this is the value. This is the value.
I hear you. But ultimately, we're talking about the entire analysis from start to finish. And the number that you're going to do depends on parts of the sequence.
It varies every time.
That's right. And so because of that, if you're worried about overall type 1 error rate, you've got to have an understanding of how many tests there are going to be in an analysis. And you just can't have that. It's a sequential analysis approach. So you can't necessarily get that. But let's not worry about it. You can split hairs, and you split hairs with that with the reviewers as well. You take if you want to do that, go ahead, take it up with the reviewers of the paper you submit to. The hypothesis testing is maddening. It's just, I like the Bayesian approach, looking at information, but we don't see that whole lot of that yet. Well, I have this dream of teaching this class in a Bayes set since either next year or something like that. Although I may end up teaching multi-level next year, so we'll see how that goes. Anyone want to take multi-level?
Yes.
Yeah. All right. There we go. There's a few of you.
Yeah, while I stay here, yes, please.
Okay, gotcha. So, all right. The next step is to check for the factor. So now we've done all that. We've established that the set of parameters, at least there's a lot of parameters that link the two scales across groups. So we can say, hey, these two things are these two factors are the same for these male and female here. Let's go and see if there's a difference in the structural model, if the factor means are different or the factor variances are different. And the way we do that, again, now we get to structural invariance. The previous model we just ran, the one that we're going to select, was residual estimates 1 because it fit the best. Residual estimates 2, when we fixed the covariance to be equal, it didn't fit as well. So we're going to take residual estimates 1. Now in residual estimates 1, the variance and the mean for the factors is separate. So if we want to test the variance for the factors, we just constrain the variance. Right? We can constrain the variance to be equal, run that model, and get a test using the likelihood ratio test. So let's think about how this works. The factor variance before was set to be estimated. If we wanted them to be equal, we need some type of identification method, so we're going to set it to be equal to 1. These are the same amount of variance in each group. We run the analysis. I did not spit out everything else because I don't think you need to see the outputs, but what you're going to see here is the p-value is 0.315. 1 degree of freedom test, that means one parameter is different between the two models. The parameter that's different is we've just taken the factor variance and locked it to be 1 for both groups. So this tells us that the factor variances are roughly the same in each group. All right, let's take a look at the factor mean. We do the same process for the factor mean. Again, we have to set it to a fixed value of 0. And that means it had, because we're trying to identify it. And what does that factor mean end up being? How was here's all the output for it, blah, blah, blah. In this test is pretty nice because ultimately, well, here you can see the factor mean itself is also not equal. They don't differ, doesn't differ right here. Now that last test actually could have been done a little bit more concisely up here. Like if I take the structural variance and I just look at the output from it, where the factor variance is set to be equal. No. This is me getting loopy coding this. I will repost this later. If I look at the output here, the variance for female is 1, the variance for male is 1. We saw this with the likelihood ratio test. This model fit the same. Let's take a look at the means. The mean for male or female is 0. The mean for male was estimated at -0.9094. But here, this has the test already included with it. There's your p-value that you need to look at. So it's telling us here that males and females do not differ with respect to this factor. And there's the anticlimactic ending of this study.
Not necessarily a bad thing.
No, could be okay.
Traits more universal than we thought.
There you go. But yeah, there's a write-up at the end as well. Now, I know we're out of time, so I'm going to have to stop here. Next time, what I'll do is we're going to talk about the next example, which is the longitudinal invariance example over time. And so we'll bring that up because the code for it's slightly different. We don't use the multi-group syntax for it because we have now, we have the same people showing up in our data. So we're actually going to create multiple factors instead of multiple groups. But then the example 3, which we probably won't have time to get to, example C, I believe it is this version of the analysis, but with weighted least the categorical data. What you're going to see is almost identical to this right here. In fact, it is identical to it. We do the same process: scalar, metric. We actually skip residual because it doesn't exist, and then we go to factor. So, okay, I will stop here. And if you have questions, come talk to me after class. Thanks, everybody.